NASA's Solar Dynamics Observatory just picked up a large coronal hole on the Sun, and it's currently rotating into a position where it's pointed almost directly at Earth. In fact, the NOAA's Space Weather Prediction Center has already put out a forecast for exactly what that's going to do to us over the next couple of days. And in this video, I will be breaking down everything you need to know. Now, let's get into it. The Sun's outer atmosphere, the corona, is normally threaded with closed magnetic field loops. Picture arches. The magnetic field comes up out of the surface at one point and loops back down somewhere else nearby, and plasma gets trapped inside those loops, held there by the magnetic tension. That's most of what you're looking at when you see a normal, bright, structured corona. A coronal hole is a region where that pattern breaks. Instead of looping back down, the field lines stay open, stretching straight out into interplanetary space instead of curving back to the surface. And when the field is open like that, plasma isn't trapped anymore. It just streams straight out along those open lines, unopposed. That outflowing plasma is what we call fast solar wind. And coronal holes are, structurally, where the Sun's fast solar wind actually comes from. This is why the imaging matters so much. SDO doesn't see this in visible light. It sees it primarily through an instrument called AIA, the Atmospheric Imaging Assembly, which images the Sun in several specific extreme ultraviolet wavelengths tuned to different temperatures of solar plasma. In those EUV channels, a coronal hole shows up as a darker patch because that region of the corona is cooler and less dense than the plasma-filled loops around it. The material's escaping instead of sitting there radiating. So when people say, a hole opened in the Sun's atmosphere, what's actually being described is a patch of the corona that went dark in ultraviolet because its magnetic topology flipped from closed to open and let the plasma drain out along it. It's not a wound. It's closer to a vent that opened up. Now, coronal holes aren't rare or exotic on their own. They're actually a permanent feature of the Sun. They're just usually concentrated near the poles, where they're basically always present to some degree. What makes this particular event newsworthy isn't that a coronal hole exists. It's that this one is large, and it's positioned at a latitude and longitude where its outflow is going to sweep across Earth's position as the Sun rotates. And that's an important distinction from something like a solar flare or a coronal mass ejection, because those are explosive, one-off events. Something destabilizes suddenly and blasts material outward in essentially one direction, once. A coronal hole is the opposite. It's a standing structure that can persist for weeks to months, and because the Sun rotates roughly every 27 days as seen from Earth, a long-lived coronal hole sweeps past our position over and over, once per rotation, producing a recurring stream of fast wind instead of a single pulse. Solar physicists actually have a name for this recurrent cycle, the Bartels rotation, named after the German geophysicist Julius Bartels, who back in the 1930s and 40s did a lot of the foundational work on classifying recurrent geomagnetic disturbances tied to solar rotation, and who, not coincidentally, is also the person credited with devising the KP index itself, which we'll get to in a second. When that fast wind stream catches up with the slower, denser solar wind ahead of it, because the Sun's wind isn't uniform, there's a slow background wind and then these faster streams punching through it. You get a compression region at the leading edge, called a corrotating interaction region, or CIR. That compression is often where the real geomagnetic effects get amplified, because you're not just getting fast wind, you're getting a pressure pulse as the fast stream plows into everything ahead of it. So here's the actual forecast, with the mechanism now in place to make sense of it. On July 21st, NOAA's expecting unsettled-to-active geomagnetic conditions, KP somewhere in the 3 to 5 range, as the leading edge of this stream starts arriving, with solar wind speeds around 450 kilometers per second. For context, the Sun's regular slow wind usually runs more like 300 to 400 kilometers per second, so 450 is already a meaningful step up. Then on July 22nd, conditions are expected to escalate to G1, that's minor storm level, KP 4 to 5, with a real chance of tipping into G2, moderate storm territory, if the wind speed peaks the way current models suggest, up around 700 kilometers per second. Let's actually unpack the KP index for a second, because I think people throw the number around without knowing where it comes from. The KP index isn't measured directly, it's derived. It's a composite built from a global network of ground-based magnetometer stations, roughly 13 of them scattered around the world at mid-latitudes, each measuring how much the local magnetic field is being disturbed relative to a quiet baseline. Those readings get standardized and averaged into a single planetary index, running from 0 up to 9, updated every 3 hours. Bartels introduced the modern version of this scale back in 1949, and it's been the standard shorthand for global geomagnetic disturbance ever since, which is honestly kind of wild, that we're still using a system designed before satellites even existed, because the underlying physics of how disturbed is Earth's magnetic field hasn't changed. The G-scale that NOAA layers on top of KP is more about translating that number into practical consequences. G1, minor, is KP5, mostly just weak power grid fluctuations that nobody notices, and Aurora pushed down to higher than usual latitudes. G2, moderate, KP6, starts to include voltage alarms on some long transmission lines and Aurora visible somewhat further from the poles. It climbs from there, G3 strong, G4 severe, up to G5 extreme, which is genuinely rare and is the territory of things like transformer damage and satellite anomalies. This event, forecast at G1 with a chance of brushing G2, sits right at the bottom of that scale. It's real, it's measurable, but it is nowhere close to disruptive, which is probably a good moment to bring up the comparison people actually want, which is the Carrington event. In September 1859, astronomer Richard Carrington observed an enormous solar flare, which was followed just under 18 hours later by the most intense geomagnetic storm in recorded history. So intense that telegraph systems across Europe and North America failed. Some operators reported sparks jumping from their equipment, and aurora were visible as far south as the Caribbean. That event is estimated to have been driven by a coronal mass ejection, not a coronal hole stream, and that distinction matters a lot for understanding why this week's forecast isn't remotely comparable. A CME is an explosive ejection of billions of tons of magnetized plasma, launched outward in a single violent event, and when a fast, well-aimed one hits Earth, it can slam our magnetosphere hard enough to induce the kind of extreme geomagnetic response Carrington's telegraph operators experienced. A coronal hole high-speed stream is a much gentler, sustained push, not an impact. Think of the difference between being shoved once versus standing in a strong, steady wind. Both can move you, but they're not remotely the same kind of event, and that's exactly why NOAA's forecasting G1 to G2 here, instead of anything resembling a Carrington-level warning. Now the fun part, or at least the part everyone actually wants out of a story like this, Aurora. Why does any of this produce aurora at all? When that solar wind plasma reaches Earth, it doesn't just plow straight into the atmosphere everywhere, because Earth has a magnetic field that mostly deflects it. But near the magnetic poles, the field lines curve down toward the surface, and that gives charged particles a path to funnel down into the upper atmosphere, where they collide with oxygen and nitrogen molecules and knock electrons into excited states. When those electrons drop back down to their normal energy level, they release that energy as light, specific wavelengths depending on which molecule and which altitude, which is why aurora comes in that recognizable green, from oxygen at around 100 to 300 kilometers altitude, and the deeper reds and occasional purples from nitrogen and from oxygen at higher altitudes. A G1 or G2 storm pushes the ring of visible aurora activity down from its usual home near the poles to somewhat lower latitudes, which is why NOAA's outlook specifically flags places like northern Scotland and southern Alaska as having a shot at minor auroral enhancement this week. Here's the honest caveat, though, and I think it's worth being upfront about instead of hyping it. This is the middle of July. If you're in the northern hemisphere, at those higher latitudes, you're dealing with very short nights right now, nautical twilight, that barely gets properly dark at all. So even with KP ticking up into G1 or G2 range, actual visibility is going to be limited just by the calendar. The geomagnetic activity is real, and the forecast numbers are solid. But don't clear your schedule expecting a big visible aurora show out of this particular event. The space weather is legitimate. The visual payoff is going to be modest. What I actually find more interesting than the storm itself is what this tells us about why events like this are showing up more often lately. And that comes down to where we are in the solar cycle. We're in solar cycle 25, which had its peak, its solar maximum, somewhere around 2024 into 2025, when sunspot numbers and flare activity were running high. Once a cycle passes its maximum and starts heading toward minimum, the character of solar activity shifts. Big, dramatic sunspot-driven flares and CMEs become less frequent, but coronal holes tend to become more prominent and longer-lived, particularly at lower latitudes where they can more easily rotate into an Earth-facing position. That's a well-documented pattern across previous cycles, not a one-off guess, and it's basically why space weather forecasters expect this specific flavor of story, recurring coronal hole high-speed streams, to become more common as this cycle continues its decline. It's also worth appreciating what's actually making a forecast like this possible at all, because it's not guesswork. SDO's imaging tells forecasters days in advance that a coronal hole is rotating into position and roughly how large and how open its magnetic structure is, which is enough to estimate what kind of wind speed to expect. Then, closer to actual arrival, spacecraft sitting out at the L1 Lagrange point, roughly 1 million miles sunward of Earth, spacecraft like ACE, DSCOVR, and more recently IMAP sample the actual solar wind in real time as it passes by, which gives forecasters a final, much more precise warning window, typically somewhere in the ballpark of half an hour to an hour before that wind actually reaches Earth's magnetosphere. That's the same basic pipeline: image the source, then confirm in situ upstream. That would give us warning if something genuinely dangerous were inbound, instead of a routine minor storm. The system doesn't care whether the event is exciting or not. It's running continuously either way, and that's honestly the more impressive part of this whole story to me. So, to pull it all together, this isn't a hole ripped in the sun. It's a region of open magnetic field, letting the sun's fast solar wind escape, and it's rotated into a position facing Earth. NOAA's forecasting unsettled-to-active conditions on July 21st and a minor, possibly moderate geomagnetic storm on July 22nd, driven by wind speeds that could reach 700 kilometers per second. If you're at high latitude, you might catch a bit of aurora, but midsummer's short nights are working against good visibility this time around. And because we're on the declining side of solar cycle 25, this is very likely not the last one of these we'll see this year. What do you think is really going on out there? Leave it in the comments and stay with us here, because today, the space world just got stranger. Thank you for watching. See you in the next one.